Section 6.7, modeling with exponential and logarithmic functions. Okay, our objective for today is we're going to classify data sets. What type of data is it? Is it linear, quadratic, exponential, logarithmic? We're going to write exponential functions, and then we're going to use our technology resources, our graphing calculator, to find exponential and logarithmic models. Okay, so first we need to talk about our idea of finite differences. This is what we did earlier, way back in chapters, 2, 3, and 4. Here I'll show you what I mean by our finite differences, where we were talking about it before, where if our x's are all equally spaced, if we all go up by 1s or by 2s, if our x's are equally spaced, we can look at the differences between the y's to determine which type of function it fits, what type of function it is, what type of function will model that data. Okay, again, if the first differences are all the same, then it's linear. If the second differences are all the same, then it's quadratic, or to the second, and so forth. If the third differences, then it'd be to the third, and so forth. Remember doing that? Way back, this is chapter 4, I believe, where we did it. So that's our idea of a finite difference. A finite difference, if the finite differences are constant, then it will model it'll be a polynomial function. For example, a linear one, that's the power of 1, quadratic, cubic, so forth and so on, dot, 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 fourth power, fifth power, so forth. Okay. To tell if a data set is exponential, instead of subtracting or taking the differences, that's again subtracting the y values, an exponential will have a constant ratio or a constant division between the two. So if the division is constant, okay, between consecutive data points, then we know it will be an exponential data set. So then we know it will be an exponential model. Okay. The example the book gives you, as we'll look at that one briefly before we do another example, is, again, if we have equally spaced x's, -2, -1, 0, 1, 2, 3, 4, if you notice between each of these y values, we multiply by 2. So if I was to divide the previous y by the one in front of it, we'd get 2. 2 divided by 1 is 2, 4 divided by 2 is 2, 8 divided by 4 is 2, 16 divided by 8 is 2. So I have a constant ratio. I multiply by 2 each time, which tells me that this is going to be an exponential function with a common ratio of 2. Okay, whereas here, if again, my x values go up by 2 each time. So here, though, there's not that common ratio. Instead, there's a common difference. So if there's no common ratio, then we want to go and look for common differences. Okay, so first thing first is to always look for that constant ratio. Okay, for here example. Okay, if we're looking at, we want to determine the type of function represented by each data set. So first of all, look at my x's, make sure we go by the same amount each time. We do. So I'm going to look for that common ratio. I'm going to take all the previous and divide it by the one in front of it. So I'm going to take 81 and divide it by 243. We get 0.3. Now I'm going to take 27 and divide it by the 81. 0.3. Take the 9 and divide it by 27. We get 0.3, which is 1/3. So I multiply by 1/3 each time. Multiply by 1/3. Multiply by 1/3, okay, to get from one to the next. So since this has a constant ratio, a constant division, I know it's going to be an exponential. Determine the type of function, it's going to be an exponential function because of that constant ratio. Okay. So let's go ahead and let's look at part B. Again, let's look for that constant ratio to see if it's exponential. Take 5 divided by 13. 0.38, take 13 divided by the 5. No. So I know it's not exponential. So now let's look at common differences and see if I can't get a finite difference to figure out if it's linear, quadratic, cubic, and so forth. So let's do the common difference. So I'll take 5 minus the 13. So here we get this common difference is -8. Here this difference is just 8. This one is 24. 40, and then 56. So the first differences aren't the same. So let's keep going. Let's do the next differences. So we're going to take 8 minus negative 8, which is 16. 24 minus 8, which is 16. 40 minus 24, so far so good, which is 16. And then 56 minus 40, which is also 16. So my first differences weren't all the same. My second differences were. So this is my second differences. Since the second differences are all the same, we know this is going to be to the power of 2 or a quadratic function. Because we're to the power of 2. Okay. All right, on to example 2, actually writing an exponential function. Okay, so here, for this extra example 2, this is very similar to example 2 in your book. I want you to write an exponential function, so they want it y equals a times b to the x. So our job is to figure out a and figure out b. Okay, so what is a and what is b in this function? Whose graph passes through the points 110 and 340. So I have a graph over here if we need it. I don't think I'm going to graph these. Well, I guess we can if we were to graph them. Let's count by ones on this way. Let's count by 5, 10, 15, 20. Let's count by fives this way. So we need the point 110, 110, and then 3, 1, 2, 3, 40. So 5, 10, 15, 20, 25, 30, 35, 40. So it's kind of going to be a curve that curves like that. Again, it's exponential, so it's going to be that nice, that curve. So I want to figure out the function that goes through those 2 points. Okay, so first thing I'm going to do is I'm going to write my 2 points down. We have the point 110 and the point 340. Those are x's and y's. This is an x of 1, a y of 10, an x of 3, a y of 40. So I'm going to plug these in to this thing for x and y. So if I plug these into this one, I'd have y is 10 equals a, I don't know a, b, I don't know b, but I know my x is 1. So 10 equals a, b to the 1. Well, b to the 1 is just b. So really we have 10 equals a times b. Okay. And then let's do the same thing with this one. So now my y is 40 equals a times b, and my x is 3. So 40 equals a times b to the third. So now I need to put these 2 equations together to figure out a and b. So I'm going to use substitution. So I'm going to solve one equation for one variable. Well, let's see, this one has a cube in it, which is a little harder to solve, so let's go with this one. Let's solve this. Let's solve it for, I don't know, solve it for a. So if I solve for a, I would divide both sides by b. So then a is equal to 10 over b. Now I can substitute that up in here for that. So I have 40 equals, my a is now 10 over b times b to the third. Okay, so let's simplify this. So I have b to the third over b, so I'd have 40 equals 10 b to the second. Divide both sides by 10. So 4 equals b to the second. Take the square root of both sides. So b equals plus or minus 2. Okay. All right, well, we notice this thing is increasing. It's going up. So that tells me that the negative 2 won't work. So if my base is negative 2, what's going to happen? It's going to go down. Again, because this is an exponential, this is a growth, an exponential growth. This tells me both of those have to be positive. So my b is just going to have to be just the 2. The negative 1 won't work. And then now we just need to find what we know b, but again we also need to find a. So now I need to find what a is. So to find a, well here, a is equal to 10 over to b. So a would be equal to 10 over b, which is 2, so that makes a 5. So my exponential model, write an exponential function of the form, so it's going to be y equals, my a is 5, times my b is 2 to the x. So if I was to graph this function, and my y equals 5 times 2 to the x, okay, it should go through the point 110, we trace it, goes through the point 110 and the point 340, which it does. So there it looks like there's my model. 5 times 2 to the x. Okay, next. Sometimes data doesn't exactly fit a model, but it can be close. We can use a model to approximate. So sometimes we need to do more of an approximation, and really that's how real life data works. Real life data, if you're talking about data as far as sales or the growth of a population or anything like that, we use approximate. So to do that, we're going to use our calculator and our stat functions to model data. So here, example 3, a store sells basketball hoops. The table shows the number Y of hoops sold during the Xth year that the store has been open. So after 1 year the store was open, they sold 17 basketball hoops. After 2 years, they sold 31 basketball hoops, and so forth. We want to write a function that models that data. So first, I'm going to plot this data in my calculator. So I'm going to go to Stat, Edit, and I want to put these in list 1 and list 2. So I'm going to arrow up, hit clear, arrow down to delete my lists. Clear, arrow down. So now list 1, I'm going to put those points in. 1, enter, 2, 3, 4, 5, 6, 7. So there's my x's. I'm going to arrow over, put in my y's. 17, 31, 50, 85, 156, 274, 498. Okay, so it just says write a function that models the data. So first let's look at the data and see what kind of function it might fit. Okay, so let's go ahead and let's look at the data. So I need to turn my stat plots on. So I'm going to go y equals. I'm going to delete whatever's there. And I'm going to arrow up and turn my plot on. Okay, just arrow up to 1, plot 1, and hit enter. As long as your plot is set up accurately, you can turn your plots on that way. To double check your plots, let's go to second stat plot. Plot 1 is where we want to be, and let's double check. It's a scatter plot, just dots. My x's are in list 1, my y's are in list 2. We want it to mark it that way. Okay, it looks good. So we graph it. Oh, we can't see all our points. We need to change our window. There's a zoom stat option, 9, to help us see our data. Okay, so this looks maybe quadratic, but it really starts out slow and gets big really fast. And if we think back to our exponential models, isn't that what our exponential models look like? Started slow, pretty low, and then got big really fast. Yeah, if we look at our exponential models here, say this one again, starts slow, really fast. So I think this might be an exponential. So let's do an exponential model for this. So let's go stat. Now we want to calculate. So we're going to arrow over to calculate. And we want an exponential model. Your calculator can do them. It's exponential regression right there. So we hit exponential regression. List 1, list 2. We want to put that in y1, y bars function, and then calculate, and there's our exponential model. Okay, so we write that model down from our y equals, and we get 9.6 times 1.75 to the x. And we can use that model then to make examples. So right now we're going to ignore example 4 over here. I'm going to come over here to extra example 5. So it says use a graphing calculator to find an exponential model for the data in extra example 3, which we did. Okay, and then use each model to use the model to predict the number of hoops sold in the 8th year. So we can actually use this model to predict the number of hoops sold the 8th year. So I'd like you to go ahead and do that. Okay, we'll discuss that in class. But now let's move on to example 6. So here we have the height of a tree increases with age. At the time of planting, the tree was 1 year old. The table shows the height in feet of the tree at specific ages. Use a graphing calculator to find a logarithmic model of the form h equals a plus b, the natural log of t, that represents the data. Estimate the height when the tree is 3 years old. So first things first, we're going to come and put our data points in. Okay. So 1, 4, 6, 10, 12, and 14 are our x's, age, t, our height, our age. And now for our y's, let's put the height, 5.5, 15.5. 7.5, delete that last bit, 23, 25, and 26. Okay, so now, there are our data points. So let's go ahead and let's look at those data points. Let's go to our y equals, we can delete that from before. Okay, and let's zoom 9. So there's our stat plot. Okay, so we want to create a logarithmic model for this. Okay, so if we go to our stat button and we want to calculate, your calculator can actually do logarithmic models. Okay, it is the LN regression. Okay, so a lot of times people accidentally use that for linear. It's not linear. It's a natural log regression. So list 1, list 2. Let's put that vars. Let's put that in Y1, and let's calculate. Okay, so we get our A is 5.3 plus my B is 7.8, the natural log of X, and my R value is 0.997, which that's pretty close to 1, so we're pretty good there. So my model ends up being, if we write this down, Y equals, my A is 5.31 plus my B is 7.82, the natural log of X. I can only do natural logs, so we can't do a log any other base, but it says now estimate the height when the tree is 3 years old. So now let's go ahead and let's trace. So there's our model, fits the data pretty good. Let's trace, but I don't want to trace on plot 1. I want to trace, I'm going to arrow down. I want to trace on my Y1. And we want to know, estimate the height when the tree is 3 years old. So it's going to be in between this 1 and 4. So when the tree is 3, should be approximately 13.9. So again, this is approximately 13.9, and this is height in feet. So there is our logarithmic model, and there's our approximate height. Okay, so now on this next page, there are some extra practice problems. Okay, I want you to do 1 through 6. These are, instead of the your turn, the monitoring progress, these are the your turn. You're going to do these extra practice. 1 through 6, and then on the back page, okay, I want you to do part A. I want you to skip part B. I want you to do A, part C, and part D. Okay. So A, C, and D. Okay, good luck.